So we are on the last topic from particle kinematics. So first was the derivative relationships between acceleration, velocity, and position. Second was the chain rule. Third was relative motion. And now we're going to talk about circular and spherical motion. Okay, so the first thing we have to do is define the angular velocity vector. And we're always going to represent the angular velocity vector as a lowercase omega Greek letter. First, we're going to talk about it for circular motion, and then we're going to talk about how that relates to spherical motion. In circular motion, so imagine that this is that we have a circular motion like this going around a center here. I'm picturing a coordinate system. So this is like on the X, Z plane. Okay. The magnitude of I don't know why that door is locked. So the magnitude of the angular velocity vector is, we're going to call it the angular speed. And the angular speed is a scalar. The magnitude of a vector is a scalar. And I'm going to call it capital omega, but it's not a vector. It's just a number. And that is equal to the derivative of the angular position with respect to time. And that's just always going to be a positive number. So we don't have to worry about directions or anything. Okay. In order to define a vector, you need to define two things, the magnitude and the direction. And so the direction follows the right-hand rule. So like if you're, so let's see, for something going around in this direction, the right-hand rule says, let me move this down a little. Curl your fingers in the direction of the circular path. And then your thumb points in the direction of the vector. Okay, so your thumb is always an axis that the direction of the angular velocity vector is always an axis that the circle is going around. Okay, and which direction along that axis it is comes from the right-hand rule. Okay, now what about if you have spherical motion instead. So circular motion is happening in a plane. Spherical motion is just, you can imagine it as motion around the shell of a sphere. It's in 3D around the shell of a sphere. In other words, it's a 3D motion where the radius stays the same, but it can go anywhere. It's like a dog tethered to a thing in space, It can go anywhere in this sphere, anywhere along the edge of this sphere, not inside the sphere. Okay, well, as an analogy of how to think about this, that for a curve in 2D, the smaller the time interval, the more that curve resembles a line. And if you take the limit down to an infinitesimal time interval, what you get is the tangent line, right? So similarly for spherical motion, the smaller the time interval, the more that path looks like a circular path in a single plane. So the more the path resembles a circle in a single plane. Okay. So in the limit, it is a piece of a circular motion. And then the definitions follow what we talked about with the circle. Okay. So that's the definition of the angular velocity vector. It's always the direction follows the right-hand rule. It has to do with the speed at which the angle is changing around a circle. Okay. So let's just do a couple examples to try to wrap our heads around this. I'm going to think of this as circular motions. So for the first one, let's think of a coordinate system like this. X, Y, Z coming out of the page. And let's say that the path is, so it's a circular motion going around the y-axis like this. And let's say that the object has a constant speed of rotation of 1 revolution per second. What's the angular velocity? Okay, well, 1 revolution is 2 pi radians. So we're going to go 2 pi radians over 1 second. And so we get 2 pi radians per second. And that's our angular speed. And now we have to think about the direction, and that's the right-hand rule. So curl your fingers in the direction of the circle. You can see that your thumb is pointing in the y direction, the positive y direction. So the direction is positive y. So the right-hand rule says the direction is the positive y axis. So the omega vector, the angular velocity vector, is 0, 2 pi, 0 radians per second. Okay, so let's do one where it's not in the direction of a coordinate axis. So let's say this time, so my coordinate axis is going to be x, y, z coming out. But this time I'm going to do a rotation about an axis like this, where this angle is 20 degrees. And the rotation is like this. And let's say that the rotations are happening at 5 rotations per second. What's the angular velocity vector here? Okay, well, we have 5 rotations per second. So to get the angular speed, we're going to go 5 times 2 pi radians divided by 1 second. And so that's 10 pi radians per second. That's the angular speed. And now we have to think about the direction. So according to the right-hand rule, if I curl my fingers in the direction of that rotation, my thumb is pointing along this black line from bottom towards the top. And so now we have to figure out a way to represent that. And we can do that as a unit vector. I mean, really, that's what we did before. The y-axis was a unit vector in the direction of the vector. So
the line parallel to the axis, or is it only like off the only off from the y-axis?
It's from the negative y-axis, yeah. And so the axis that we're talking about if I put the tail at the origin, is this, okay, where this is 20 degrees. And so to come up with a unit vector in that direction, that's going to be, from the positive x-axis, this is positive 90 plus another 20. So this is going to be cosine of 110 degrees, sine of 110 degrees. And that is negative 0.342, positive 0.940. And I guess we're doing it in 3D. Okay, and now put these two things together. The magnitude of this rotation, which was 10 pi, times this unit vector, and let me just multiply that out quick. So I'll just give this to you in a decimal. And you get negative 10.74, 29.530. And this is in radians per second. Yep.
What happens if we were to use radian units for the trigonomic function? So just put in like whatever it's 100 degrees is in units of pi?
Yeah, that's fine. It comes out the same.
Well, I guess that would just be the extra work.
Yeah.
I figured I wouldn't mind. Yeah.
Any other questions? Okay. So that's the angular velocity. Anytime you are trying to understand what's going on with the angular velocity, this isn't very much information, but all the information you need is here. So go back and read this and, it's like, where's Waldo? Like, where's the bit of information that I need to interpret? Yes?
Well, I'm just curious, on the x-axis, what should we assign? Because...
Oh, okay. So so there are a bunch of ways to do this trigonometry. You could make a right triangle here, and maybe that's what a lot of people would do. I tend to just always I take my angle from the positive x-axis, and then whatever that counterclockwise angle is, I know cosine is the x-axis and sine is the y-axis.
Yeah, if I do like sine of 20.
But yes, you can totally do it that way. Yep, you get the same thing. Any other questions? Okay, well, now we have to define the angular acceleration, which is also a vector. And we're going to use the Greek letter alpha for that, lowercase alpha, like a goldfish. This is Jesus's favorite rotational quantity. And that was a joke. I don't know about.
What was the punchline?
Like, haven't you seen the cars with that symbol on the back? Like, that's like the Jesus fish.
Really?
Yeah. Okay, so angular acceleration. There's not a good way to have intuition about it without also thinking about the angular velocity. So first of all, we'll think of the definition of angular acceleration. So this is defined as the time derivative of the angular velocity. That's a double, which you can also write as using the dot notation. And just like the relationships between acceleration, velocity, and position in translational quantities, don't think of this as just the plain derivative of the angular velocity. It has to be with respect to time, okay? You can use the chain rule on this the same way that you can with translational quantities. And there's a problem or two where you'll have to do that in this class. But it's the derivative with respect to time. And here is the way you can think about this intuitively. For circular motion, omega and alpha are always parallel to each other. And if they're in the same direction, the rotations are speeding up. And if they're in opposite directions, the rotations are slowing down. If you're in spherical motion, it's a little more complicated. They're not always parallel. They're not ever parallel, or it would be circular motion. You can think of the angular acceleration as having a part that's parallel to the angular velocity and a part that's perpendicular to the angular velocity. And I'm going to think of these as, so the part that's parallel to the angular velocity, I'm going to call alpha parallel. The part that's perpendicular, I'm going to call alpha perpendicular. And if alpha parallel is in the same direction as the angular velocity, then you think this rotations are speeding up or slowing down? Speeding up. So that works the same as with circular motion. Bless you. And if the angular acceleration parallel is in the opposite direction of omega, then these rotations are slowing down. And then, so what's the alpha perpendicular part doing? This determines how quickly the axis of rotation is changing. So you get sort of how quickly it's moving away from circular motion into other planes. Okay. Okay, so that's all for intuition. Really, you won't need that intuition in this class, but if you're curious about it, that information is here. You can sort of try to wrap your head around it. But mainly, we're just going to be using these things, given these things in problems, and using them to calculate accelerations of particles. So for a particle moving in circular or spherical motion, the velocity of the particle is equal to omega crossed with r. And I'll be very specific about what these things mean in a second. And the acceleration of the particle is equal to alpha cross r plus omega cross quantity omega cross r. These are going to be super key equations that are going to come up all the time in this class. And that r vector is the vector from the center of the circular or spherical motion to the particle. That definition of R is really important, and that's going to come up on quizzes more than once. Okay, so remember that. Omega is the angular velocity vector, alpha is the angular acceleration vector. You've used equations like this in Physics 1, you just didn't probably use it as often in the full vector form. In a way, this is easier because it does all the directions for you. This is so what part of the acceleration do you think that is? Think of it, this is a circular motion. So what does that look like? This is the tangential acceleration. And then what does this one look like? This is the centripetal. So I guess, yeah, that radial, right, centripetal, we'll call it in this class. Bless you. This acceleration equation is going to be especially important to us because remember that acceleration is the skyway to Newton's laws. No matter what you want to know about the kinematics or whatever, what you want to know about the kinetics, the only way to get from one to the other is through acceleration. And so there's a memory device for this acceleration equation. I made this up. It's trademarked. All ripe watermelons will rot. Okay, so A for alpha, R for R, W for omega, W for omega, R for R. Okay, and somebody once complained that was really pessimistic and they preferred all ripe watermelons will rock. So you can use that too. Okay, so let's see this in action. See how this works. Yeah.
If the radius changes, will that be?
Well, okay, so that's an important thing here. These represent a single instant. So that R vector is, if a thing is moving, that R vector is changing all the time. But we'll just use the instantaneous R vector. As far as the magnitude of the R vector, that can't change, or else we're not in circular or spherical motion. But the vector can change. Okay, so let's do an example. So picture a child on a playground carousel. I don't know if you guys have ever seen playground carousels. They were like the source of 80% of childhood injuries when I was a kid. They're these giant steel things, and you put this poor kid on there, and then you zip it around and make it spin in circles. And
I think I've seen a couple of them.
yeah, it was like a favorite torture device of schoolyard bullies when I was a kid. But anyways, there's a child on one of these carousels. And this thing has a radius of 2 meters. And at the given instant, so remember we're doing instantaneous calculations. It's rotating counterclockwise. And in 3D, counterclockwise and clockwise sort of lose their meaning unless you know what direction you're looking at something from. So I'm going to just specify that I'm talking about from above. With an angular speed of 2.5 radians per second. And at this instant, it's slowing down at 9.5 radians per second squared. And so this is what it looks like. There's the carousel. Here's our coordinate system. And this is the point that we are interested in calculating stuff for. So let's calculate the position vector, the velocity vector, and the acceleration vector of that point P. Okay, so the position vector at this instant, you can see that this thing has a radius of 2 meters. So we're just going 2 meters in the positive z direction. So this is 0, 0, 2 in meters. So my first question is, now we have the position vector. Why couldn't we just take the derivative of this to find the velocity vector and the derivative of that to find the acceleration vector? We can't. Why not? Yeah, right. This is not a function of time. This is just a snapshot at an instant. So if you take the derivative of this, you get zeros. But that would only work if this was the position at all time, And so yeah, we're not going to be able to do it that way. So for the velocity now, we know that the velocity vector is equal to omega cross r. Let's figure out what omega and r are. So omega is going to have a magnitude of 2.5. We have to think about the direction of that rotation and use the right-hand rule to get the direction of the vector. So from above, it says it's rotating counterclockwise. So move your fingers in the direction of a counterclockwise rotation. Your thumb is in the positive y direction. So this is going to be 0, 2.50. So omega is 0, 2.50. This is in radians per second.
I think you know that the radius was on the C direction. It is giving on the problem.
Say that again?
The radius
Yeah,
is 2 meters, right?
2 meters, yep.
Yeah, how do we know that is in the C direction? I'm not
The position?
Yeah.
Okay, well, that point P here at this instant is it's just from the figure.
Oh, okay, so
You can,
it's
so
given on the problem.
at the next instant, it would be something else.
Okay.
But at this instant, it's just pointed straight in the Z direction.
Could we take a different direction, or is it this?
What?
Could we pick a different direction?
Yeah, if I don't give you a coordinate system, you can pick your coordinate system. Yep. And now the R vector. So think of the definition of the R vector. It is from the center of the circular motion to the point we care about. So in this problem, that is from the center of the circle here to P. So that's going to be the same as the position vector in this case. Okay. So R is equal to 0, 0, 2. And I have a question about that. Does R always have to be the same as the position vector? No, otherwise I would just have the position vector in the equation, you know. So remember, the position vector is a vector that goes from the origin to the point you care about. Okay, the R vector goes from the center of the circular motion to the point you care about. So the only time that P and R are the same is when the origin is at the center of the circular motion. If they're at different points, then those are different vectors. Question?
So then the only time that would be applied is if you had like a sheet then, so the origin is the center.
Well, it just really has to do with where you put your origin, you know. Like I could have put my origin up above and then those would have been different vectors.
Okay. Professor?
Yeah.
So, like, in this problem, the disk is like on the XZ plane. Why are we using Z instead of like X?
Yeah, I don't know. That's just how I drew it. That's all.
But could we do the exact same thing, just like the P is like 2, 0, 0 and so on?
Yeah. Yeah, if I just move my coordinate system in a different orientation, yeah, exactly. Okay, so put these in here, and now you get that V is equal to 0, 2.5, 0, crossed with 0, 0, 2. And you can just plug this into your calculator. You can use your favorite way to calculate cross products by hand. This comes out to be 500 in meters per second. Okay, so let's look at this and look at this picture and try to figure out whether this direction makes sense for the velocity vector. Well, the velocity vector is always going to be tangent to the path in the direction of motion. This thing is moving counterclockwise. And so tangent to that counterclockwise circle at that point is to the right, which is in the positive x direction. Okay. Any questions about that? Yeah.
Question, just for like the units of like crossing R with W.
Yeah.
Does it actually cancel out to meters per second, or do we just have to say that?
It does cancel out because the units of angular velocity are radians per second, and remember, radians are not a unit, you know.
Oh.
And so it's really, you can always think of radians per second as just 1/seconds, and so it does come out to be meters per second. Any other questions?
Just gonna get about the velocity being a tangent of it.
Oh yeah. Well, remember that if you have a circular motion, let's say it's going this way, the velocity vector at any point is tangent to the circle. So that's the velocity of that point. That's the velocity of that point. And in this case, the way it's lying tangent to the path in the direction of motion is in the positive x. Okay, so now let's go to the calculating the acceleration of that point. So this is equal to all ripe watermelons will rot. Sort of an existentialism kind of thing. Ashes to ashes, dust to dust. All we are is dust in the wind.
Kind of ties back to thermodynamics in a way.
Yeah, that's true. Yeah. This is the second law of thermodynamics. Yeah. Okay, so we already have R, we already have omega at this instant. We just need to come up with alpha. And what we're told is that this is slowing down at 9.5 radians per second. It's circular motion, which means it's going to be parallel to the angular velocity. So it's going to be either in the positive or negative y direction. Okay. So circular motion means that it's parallel to omega. So it's going to be the positive y or negative y. So that's the first thing we know. Then we're told that it's slowing down. So slowing down means that it's going to be opposite the direction of omega. So it's going to be in the negative y direction. So alpha is equal to 0, negative 9.5, 0. And this is in radians per second squared. So now we can put this stuff in. The acceleration of that point P is 0, negative 9.5, 0. Crossed with R, which was 0, 0, 2. Plus omega, 0, 2.5, 0. Crossed with the quantity, 0, 2.5, 0. Cross R, 0, 0, 2. Okay, so let's just go through this piece by piece. This is the one that we already did. This is omega cross R, so this is 5, 0, 0. And now we're crossing this with this. Remember, the order matters here. And so we get 0, 0. And then for the z direction, we get negative what's 5 times 2.5? 12.5. Negative 12.5. And then these two crossed are negative 19, 0, 0. And so now add these two together and you get a vector that's negative 19, 0, negative 12.5. Okay, well, this is the centripetal acceleration. And this is the tangential acceleration. Let's look at those and compare those to our intuition about what's going on. So first, the tangential. If this thing is slowing down, the tangential acceleration needs to be opposite of the velocity vector. Our velocity vector was in the positive x. This is in the negative x, so that makes sense. And now the centripetal acceleration always has to point from the object, the particle, toward the center of the circle. Well, our particle is at P. The center of our circle is the origin, where I put the origin. And so that vector from P to the center of the circle has to be in the negative z direction. And that's what we got. So those make sense. Okay. So it takes a while, I'm sure, to get used to the vector definitions and everything. But the nice thing is this does all the directions for you. You don't have to think about like the direction is centripetal and tangential anymore, which makes this very useful for programming stuff. You know, this is just a set of rules that works without thinking once you define all these things correctly.
So for setting, when you found the direction of the angular acceleration, did you just go that the motion is in like the xz plane, and then it either has to be positive or negative y?
Well, that is a way to do it. That's a perfectly valid way to think about it. I thought about it like this. So I said, for circular motion, omega and alpha are always parallel. And if the thing is speeding up, they're in the same direction. If the thing is slowing down, they're in opposite directions.
Okay.
So that's what I used. Any questions about that? Okay. One of the reasons, the biggest reason that these circular motion equations are going to be really important in this class is because when any rigid body rotates around a joint, around a hinge, or a ball and socket joint, I guess, it's moving in circular or spherical motion. If it's a hinge, it's moving in circular motion. So let's do an example like that. So let's say we have a hinge attached to a wall, and then we have a rigid body. And we're given that at the instant we're looking at, remember these are always just snapshots, this angle is 20 degrees. The length of this bar is 1.5 meters. And let's say that the angular velocity is this way at 5 radians per second. And the angular acceleration is the other way at 15 radians per second squared. And we want to calculate, so let's make that point P, and then the center of this, let's make that C. So let's say we want to calculate the acceleration of the point P, and we want to calculate the acceleration of the point C. Bless you. Okay, so first, we're going to use this acceleration equation. So acceleration is equal to all ripe watermelons will rot. And so we have to define some of these things. Let's first figure out what R is. I haven't given a coordinate system, but let's just use a standard coordinate system with X this way, Y this way. If X and Y are those directions, what direction is Z? Into or out of the page? Out, yep. Because the right-hand rule has to tell you that X cross Y is equal to Z. Okay, if the angular velocity, we're doing R first. So for that point P, we're going to go, you can think of this vector that we want. The R vector goes from the center of the circular motion, which is the hinge, to the point you care about. So that would be 1.5 times cosine and sine of 160 degrees. And you get negative 1.410, 0.5130. And now let's think about the angular velocity. We're told that the magnitude, go back. We're told that the magnitude is 5 radians per second. If you curl your hand in the direction of that angular velocity, and you can tell which is which from the units, by the way, it's going to be into the page, so negative Z. So the angular velocity is going to be 0, 0, negative 5. And now the angular acceleration, that's going the opposite direction. So curl your fingers in the direction of the angular acceleration. That's in the positive Z direction. So are these rotations speeding up or slowing down? Slowing down, yep. And so this is going to be 0, 0, positive 15. This is radians per second squared. And now we'll put this together. The acceleration is 0, 0, 15 crossed with negative 1.41, 0.5130 plus 0, 0, 15. Nope. Wrong. This should be omega. 0, 0, negative 5. crossed with the quantity 0, 0, -5, crossed with -1.41, 0.513, 0. For this one, you probably don't want to do this stuff by hand. It would. I just stopped the recording to do that. Okay, so what's going to change here for part B? The only thing that's going to change is the r vector. The angular velocity and angular acceleration stay the same. So the r vector this time, the vector from the center of the circular motion to the point we care about, is just going to be a distance of half of the length, so 0.75 times cosine of 160 sine of 160. And that is just going to be half of each of these components. So we'll have negative 0.705, positive 0.257, and then 0. And so now, these two stay the same because it's the same rigid body. And so the acceleration of the center is 0, 0, 15, crossed with negative 0.705, 0.257, 0, plus 0, 0, -5, crossed with the quantity 0, 0, -5, cross negative 0.705, 0.257, 0. I think this is just going to come out to be exactly half of the last vector we got, but I'll plug it in here. And I get positive 13.77, negative 17, 0. Which is, there's some round off error. I rounded off some stuff, but that's just half of the first one. Okay. I have two questions. No, just one question. Why would I ever want to calculate the acceleration of the center of mass of an object in this way? Yep.
Essentially, we just treat the center of mass as if, it represents the entire object. We treat it as if all force and motions.
Yeah. So, right. So the key thing is Newton's second law. When you're working with particles, you think Newton's second law is F equals ma. But when you're dealing with rigid bodies, which is what we're going to be doing pretty much this whole semester, Newton's second law really says F equals mass times the acceleration of the center of mass. Remember, a body, every point on a body, speaking in general, has a different acceleration, okay? And so you can't use the acceleration of whatever point you want in Newton's second law. You have to find it for the center of mass. And so that's going to be an important thing for us. Okay, we're going to use this technique to calculate the acceleration of the center of mass of objects pretty often. Okay, any questions? All right, that's it for today. So what we're going to do next time is you can imagine a linkage where you have another arm connected to this arm, like a robotics type thing, and we're going to use relative motion along with circular motion to calculate like the acceleration of the second arm of that linkage. Okay, that's all.